In the old days when I was a beginner, I always confused when facing the circuit to determine the base resistor value. I always wondered why we have to put a resistor at the base terminal of a transistor, but I was 100% sure that it was needed for some reason. I used to find the best base resistor value by trial and error, and luckily in most cases I found a good enough value. I wasn't aware of how it can be dangerous. In this video, I'm gonna tell you why we have to put a resistor at the base terminal of a transistor and why its value is important. Then I will teach you two approaches, a simplified method and an advanced one to select best base resistor value. Also, we will explore the data and graphs on the datasheet to find the information to select the best base resistor value. Please stay with me until the end of this video. You may have seen this figure before. It's a diode model of a transistor. Certainly you can't make a transistor by connecting two diodes like that, but this model shows that why we have to put a resistor at the base terminal of a transistor. Now I'm asking you, what will happen if a voltage like 5 volts is applied to a diode directly? If the diode inside the transistor is directly connected to a voltage source without any resistance between them, one of these consequences will follow. 1. The transistor will be destroyed. 2. The voltage source will be destroyed. If the voltage source is strong enough, it will destroy this diode and eventually the transistor by delivering high current to this junction. And if the voltage source is not strong enough to deliver much current, the voltage source itself will be destroyed. In this case, which we are going to power up the base terminal using a microcontroller, the GPIO on the MCU is not strong enough to destroy the transistor, so the MCU pin itself will be destroyed. This is why we have to put a resistor at the base terminal of a transistor. So now we have reached the $1 million question. What should be the value of the base resistor? Before answering this question, it's better to know the consequences of a bad resistor value. What could go wrong if you pick a bad resistor value? A bad value for this base resistor is one that works, but there are other values that work better. A good value should put the transistor deep into saturation in a way that the transistor can't go back to the active region easily. What are the active or saturation regions, you may ask? When the transistor is off, the voltage across collector-emitter junction of the transistor is maximum and it's equal to VCC. When the transistor is saturated, the voltage across collector-emitter junction is negligible. It's a bit more than 0 volts, and the active region of operation is where the voltage across collector-emitter junction of this transistor, the VCE, is within the range of 0 volts and VCC. The transistor acts like an amplifier in the active region of operation, and it's operating as a switch in saturation region where the voltage across this junction is very low. The first thing is power dissipation. Power dissipation is product of collector-emitter voltage and collector current. Choosing a bad value for this base resistor may put the transistor in active region where the collector-emitter voltage is high. Higher collector-emitter voltage means higher power dissipation. Higher power dissipation means higher risk of transistor failure and damage. The second thing is reliability, which is so important. I mean, by using a bad value for the base resistor, maybe the circuit works when you are testing it, but in real world and real working conditions, sometimes it may fail. I mean, sometimes it may work and sometimes it may not. This is a real disaster. Imagine a fire alarm that isn't reliable. It sometimes works and it fails at other times. That's incredibly dangerous. Anyway, to ensure that the switch will work perfectly in any condition, we have to make sure that the transistor is operating in deep saturation region. The base resistor is a powerful tool to make sure that the transistor is operating in deep saturation region. There are several approaches to select base resistor. To start, I will provide 3 examples for you to work through the calculations. The first example is to select right value for base resistor to switch the simple resistive load using BC547. The second example is where the load is the 12 volt relay, and third example is to select best resistor value to switch this 2 ampere 30 volt DC motor using this TIP41C transistor. The first method for selecting best base resistance is the simplified method. These are parameters needed to find the best base resistor. IC or collector current, which is almost equal to current rating of the load. I mean the maximum current drawn by the load. VCE or collector emitter voltage, which is usually considered to be very low, say 0.2 volts or even 0 volts for simplicity. VI, the input voltage, which is the voltage that is going to trigger the base terminal. For example, if you are going to command the transistor using a 3.3 volts STM32 microcontroller, the input voltage will be 3.3 volts. The next parameter is VBE, the base emitter saturation voltage. I'm going to use 0.7 volts for simplicity. And the last parameter is HFE. Which is the current gain of the transistor. I'm going to use HFE equal to 10 for simplicity. To determine the best base resistor, we have to find the best base current. I mean this IB. I got this equation using Ohm's law. By knowing VI, VBE, and IB, the RB will be calculable. Actually, base resistor will be a function of base current. Here is an interesting point. It seems that we are looking for best base resistor value, but actually we are looking for best base current, IB. Any method or trick that leads to finding best base current will be a shortcut for finding the best base resistor value. More details later in this video. This is a basic equation coming from definition of HFE. The HFE is the ratio of the collector current to base current. From this equation, since the HFE is usually a constant and a desired number, the IB will be a function of collector current. So, to find the base resistor, we have to find the base current. To find the base current, we have to find the collector current. And to find the collector current, there may be different possibilities. Sometimes the load is a simple resistor and sometimes the load acts like a resistor. In such a case, the collector current will be calculable using Ohm's law. But if the load is not a simple resistor, you can refer to the data provided by the vendor, and if you don't have access to the vendor or to the datasheet, you can find the maximum current drawn by the load using an ampere method. If the load is a 100 ohm resistor, the IC is going to be the voltage across this resistor divided by its value. The VCC is 12 volts and the VCE is assumed to be 0.2 volts, which is pretty standard. and RC is 100 ohm. Then the IC is going to be 118 milliamperes. By using this simple formula and assuming the HFE equal to 10, the IB is going to be 11.8 milliamperes, and by using simple Ohm's law here, the RB is going to be 220 ohms. Thank God we got 220 ohms, which is a standard value, and it's available in the market. Okay, let's move on to the next example. In this example, the load is a 12-volt relay, but the current drawn by the coil is unknown. I can find the current drawn by the relay by applying proper voltage to its coil and measuring the current flowing into it. It's drawing about 28 milliamperes. In the circuit, the IC is 28 milliamperes, the IB is 2.8 milliamperes, and the RB have to be 928 ohms. We got 928 ohms for the base resistor. Since 928 ohms is not a standard value, we have to find nearest standard values to 928 ohms. By searching for standard resistor values on Google, you can find some tables. By looking at those tables, I found 910 ohms and 1 kilo ohms. 928 ohms is closer to 910 ohms than 1 kilo ohms, so I have to choose 910 ohms for the base resistor. On the other hand, I always prefer to choose a standard value that is smaller than the calculated value, because by choosing smaller values, the HFE decreases, causing the transistor to fall more into the saturation region. Anyway, let's consider the last example before moving on to the advanced method. Assume that we are going to calculate best base resistor for the circuit. Based on the information provided by the vendor, this motor operates on 30 volts, so VCC is 30 volts here, and it draws up to 2 amperes. Then the IC is about 2 amperes. Now we are going to select best base resistor in the circuit to safely and easily switch this motor using this transistor. Here we have a 3-volt battery which is going to drive the base current, and there is another power supply here to drive the DC motor. In this example, the IC is 2 amperes. So by using HFE formula, IB has to be 200 milliamps. Since VI is 3 volts and VBE is 0.7 volts, the RB has to be 11.5 ohms. 11.5 ohms is not a standard value, so we have to select a standard value that is close to 11.5 ohms. By looking at the standard value table, I found 10 ohms and 12 ohms, which are standard values, and they are close to 11.5 ohms. Both of them are okay to be used in this example, but there is another problem here. Let's look again at the base resistor. The voltage across the base resistor is 2.3 volts and it's drawing 0.2 amperes, so it will dissipate 0.46 watts, which is relatively high. We have to choose a resistor that has a power rating higher than 0.46 watts, say 0.5 watts, 1 watts, or even more. This one is an ordinary a quarter watt resistor, this one is a half watt, this one is a 1 watt resistor, and this one is a 2 watt resistor. Even though a half watt is greater than 0.46 watt, it is better to be more careful and use at least 1 watt resistor. I think it's better to use 12 ohm 1 watt resistor at the base terminal, but here I'm going to use 10 ohm 1 watt resistor because I already have it in my workshop. Everything seems okay. When I press the button, the motor starts to run. Let me remove this button and directly connect the battery to base resistor. Even when I try to stop the motor by using these pliers, the transistor is still driving the motor and doesn't jump out of the saturation region. It means that the base resistor value is good. How did I know the transistor was still saturated, you may ask? By monitoring the collector emitter voltage. While collector emitter voltage is very low, the transistor is saturated. When I increase the collector current by trying to stop the motor, VCE increases, but it is still very low. The base current is approximately constant, but when you try to increase the collector current by stopping the motor, the HFE has to increase. By increasing the HFE, it becomes more likely that the transistor will enter the active region of operation. We checked it by measuring the VCE and seeing that in high collector currents, the VCE is not significantly increasing. In this example, there is no sign of such a situation and everything seems to be okay. Anyway, we have learned the simplified method for selecting the base resistor. Now is the time to move on to the advanced method. In the simplified method, we had some default values for some parameters. We assumed that the HFE is 10, the collector emitter voltage is 0.2 volts, the base emitter voltage is 0.7 volts, etc. In the advanced method, the calculation is the same as in the simplified method, but we have to find exact and specific values of these parameters according to the datasheet of the transistor we are going to switch and the specifications of the load we are going to switch. Suppose that we are going to select the base resistor for this circuit again, this time using the advanced method. In the advanced method, we have to use the datasheet to find the exact values for the required parameters like VCE, VBE, HFE, etc. When you hear the name advanced method, you may think that the method has to be very complicated and time consuming. But contrary to its name, in some cases, the advanced method is much easier than the simplified method. I call it advanced method because we are going to use the datasheet to find specific values for particular parameters of the transistor instead of using these default values. Anyway, let's take a brief look at the datasheet of BC547. You may wonder why I use this particular transistor in this circuit. There is a video describing how to select best transistor for a particular load in the description. You can watch it to find out. This is datasheet of BC547 transistor. This is the VCEO, which is equal to 45 volts. It's enough because the maximum voltage in the circuit is 12 volts. The IC max or collector current continuous is 100 milliamperes, which is okay because the maximum current the relay draws is about 30 milliamperes. Now we have to find the values of the parameters. There are many graphs on the datasheet, and also you can find other datasheets that contains other graphs. You can use some of these graphs to select the best base resistor. Look here. I have printed this graph on another paper. It contains three different curves. The first one is collector emitter saturation voltage versus collector current when the HF is 10. Next one is base emitter voltage versus collector current when the collector emitter voltage is 5 volts. And the last one is base emitter saturation voltage versus collector current when the HFE is 10. Look at this area. Here is where the collector current is equal to 30 milliamperes, which is very close to the maximum current the relay draws. The voltage across collector emitter junction of the transistor at this point is about 50 millivolts. So the power dissipated by the transistor at this point will be something around 50 milliwatts, which is far less than the maximum power dissipation of the transistor, which is 625 milliwatts. Look here. So it's safe for the transistor to operate at this point. Also, there is a base emitter voltage here at this point. The voltage across base emitter junction will be about 0.76 volts, which is a bit more than the default value 0.7 volts. The information presented in this graph was sufficient for calculating the IB and consequently the RB, but different datasheets present the data in different ways. So you have to be more creative when dealing with datasheets. Sometimes the desired information is presented directly, making it a shortcut to determine the base resistor value. If you look attentively, you can find this graph which shows collector emitter voltage versus base current. I have printed this graph on a separate paper. You can find the base current easily by looking at this graph. Each of these curves shows the relation between collector emitter voltage and base current in a specific collector current. For example, this one shows it when the collector current is 10 milliampere. This one is when a collector current is 20 milliampere. This one 50, this one 100, and this one 200 milliamperes. Unfortunately, there is no specific curve for IC equal to 30 milliampere, which we are looking for, but you can estimate its value by the values near 30 milliamperes, like this 20 milliampere and this 50 milliampere. We can consider collector emitter voltages below 0.2 volts as an indicator of the transistor being in saturation region. So this region will indicate the saturation region. Look at these 2 points here and here. Base current more than 0.2 milliamperes will cause the load with collector current equal to 20 milliampere to go to the saturation region. Look here at this point. And the base current more than 0.6 milliampere will cause a load with collector current more than 50 milliampere to go to the saturation region. Look here. It's likely that the transistor with IC equal to 30 milliampere will go to saturation region when the IB is higher than 0.3 milliamperes. I mean, the threshold value is 0.3 milliampere in this example. So the RB for this threshold base current has to be 3.3 volts the input voltage minus 0.76 volts the base emitter saturation voltage divided by 0.3 milliamperes the threshold base current. I got 8.46 kilo ohms as the threshold RB. Note that this 8.46 kilo ohms is a threshold value, meaning that the values lower than that will cause the transistor to operate in saturation region, and the values higher than that will cause the transistor to operate in active region of operation or cutoff region. Remember, in the simplified method, we got 928 ohms, which is lower than 8.46 kilo ohms, and it guarantees that the transistor will stay in saturation region. you have to choose a value lower than 8.46 kilo ohms. The lower the RB, the deeper the transistor goes into saturation region. But you can't choose very low values for the base resistor, because choosing the base resistor below a certain value will damage the base terminal. In some data sheets, it determines the maximum current for the base terminal, which is helpful in calculating the minimum base resistor. In this datasheet, it doesn't determine the maximum continuous IB, so I can't determine the exact minimum RB, but I can guess that this transistor can withstand at least 20 milliamperes into its base. So the base resistor in this example has to be more than 127 ohms and less than 8.46 kilo ohms. It's better to choose a value between these thresholds. In this example, 4.7 kilo ohms will be a good choice. There are a lot of manufacturers, so finding a slight difference between BC547s from different manufacturers is normal. However, the rules are the same. Anyway, we have reached the final moments of this video. I hope you enjoyed this video and learned how to choose right value for base resistor of your transistors. Thanks for watching. If you enjoyed this video, please give me a thumbs up, and if you liked this video, make sure to subscribe for more.